So last week we talked about position versus time graphs. We talked about motion, how that motion is relative to other things, how you plot that, how you can use this to find the slope that'll give you the velocity. This week we're going to talk about velocity versus time graphs and the things that you can find from the information given to you in those graphs. So we know from position versus time graphs is that as the graph goes up and down, that can give you the change in your position or the change in your displacement. With the little arrow up here to signify that is the vector displacement, not distance. As the graph goes left to right, we know that that is the change in time. And we know that change in the displacement over the change in time, that's velocity. That's what we can get from this. Well, what's the difference here? We still know that the time is changing, but the velocity, when we're going up and down, the velocity is changing. So we can consider, if we compare these two, the change in the velocity over the change in time. And what is that? What do we call when we're considering how my velocity is changing? How is my rate changing over time? That is acceleration. And that's actually the definition of acceleration, how velocity changes over time. So let's look at that a little closer. So the acceleration you're probably most used to is the 0 to 60 times for cars. That's an acceleration there, even though they don't tell you the exact acceleration, they give you an idea of what it is. This is telling you I can go from 0 miles an hour to 60 miles an hour in 7.1 seconds. That's a change in velocity versus a change in time. So here our change in velocity is, of course, the difference in those two numbers. So 60 miles an hour minus 0, this is obviously an easy one since we started at 0. The change in velocity is going to be 60 miles per hour. My change in time, it took me 7.1 seconds to do so. So if we wanted to find the acceleration of a Honda Accord, then we would put the change in velocity over the change in time. Although there's one problem here that you might notice. This is 60 miles per hour, and this is in seconds. So we have 60 miles per hour divided by 7.1 seconds, but seconds doesn't go well with miles per hour because we're in hours here. So if we want to work with these units together, we need to make sure that they are the same unit. So I do know how to convert this to miles per second. That's what we worked on right in the beginning. So let's convert from hours to seconds. I know that there are 3,600 seconds in 1 hour. So I can just divide 60 by 3,600. And you know what? That comes out to be a really ugly number, so let's convert miles as well. Let's go to meters per second. I know that there in 1 mile is 1,609 meters. So miles cancel here, hours cancel here, and we'll be in meters per second. Let's find what that is. Okay, that's much better. That's about 26.82 meters per second divided by 7.1 seconds. So you'll see that that gives us about 3.78. What's the unit here? Well, we've got meters per second divided by seconds. So we have meters per second per second. We usually just call that meters per second squared. And that is the unit that we use for acceleration usually, meters per second squared. So we've got some distance per some time squared. Because it's distance per time is velocity per another time for acceleration. So that's for a Honda Accord, but for a Ferrari Enzo it's a little different. They can go 0 to 60 in 3.1 seconds. What's the acceleration there? Well, the The good thing is, since it's 0 to 60 miles per hour and we have this in seconds, we still need the change in velocity is still 60 miles per hour. So we can keep this conversion, 26.82 meters per second. Let's just change this to a 3, because these are the same numbers, but now we have a different change in time. So that should be a much bigger acceleration, in which case that is 8.65 meters per second squared. Meters per second per second. So every second I'm getting 8.65 meters per second faster. So to recap real quickly, acceleration is your change in velocity over your change in time. You can also write that as v final minus v initial over time final minus time initial. So how fast did you end up going minus how fast did you start at? That'll give you the difference in how much your time changed, or how much your velocity changed. Just like time. If you take the final minus the initial, that's how much you changed in that time. So you'll recognize that this looks very similar to the velocity formula, which also looks very similar to the slope formula. So again, you can find that on the graph here. So if I were to go here and draw a slope triangle for this, I could find my change in v, and I could find my change in t here, and I could tell you the acceleration at this point. Clearly it's 0 here since v is not changing. But this one looks negative. What does a negative acceleration mean? A negative acceleration is also sometimes called a deceleration. It just means that you're slowing down. So if I was going 30 miles an hour and then a kid chased a ball into the street in front of me, I would want to go from 30 miles an hour to 0 as fast as I could to keep from hitting this kid. That is a deceleration. That would show up as a negative acceleration because your final minus your initial. So if I said, if I was going 30 and then I ended up at 0 to keep from hitting him, that would be my initial, or my final is 0 minus my initial of 30, and I now have a minus 30 over however much time it took me. A negative acceleration, that is just slowing down, and it'll show up as a negative slope on a velocity graph.